Okay, we're going to do some Charles Law problems, and just like with any other assignment, you should pause this video and you should try these problems out yourself. When you watch somebody do any type of problem, they always make sense and they're really easy. You've got to struggle through and try to process how to get these done and then check your work and see if you've done them correct, or use the video to help you out. But don't just watch the questions. Try them out on your own first. With Charles Law, we are looking at volume and temperature. And specifically, we're looking at a before and after situation. I've got a 1 and a 1 and a 2 and a 2. This is the volume and the temperature of a gas before, and this is the volume of a gas, volume and temperature of a gas after we make adjustments of some sort. Another thing you'll notice with these problems, you see degrees Celsius in here, but we can't keep them as degrees Celsius. We have to turn everything into Kelvin. That's to make our math work out correctly, because in the Kelvin scale, 0 really means 0. There's no molecular motion, whereas Celsius, 0 doesn't really mean anything. So whenever you want to change it to Kelvin, just add 273 to your Celsius numbers to get them into Kelvin. So looking at the first problem, we've got a balloon that we are going to place into a fridge. Why are we going to do that? Well, we want to see what's going to happen. Good grief, I can't write these formulas out. We want to find out what is going to happen to the volume when I put this balloon into the fridge. So I've got V1 over T1 equals V2 over T2. So I've got to look and find out that originally my balloon is 0.50 liters. Originally it's 22 degrees, but remember I got to add 273, so that's going to be 295 K. Now I'm going to go ahead and put it in the fridge. When I put it in the fridge, I am not sure what that new volume is, but I do know that it's going to be cold. It's going to be 4, so I add 273 and 4, I get 277 K. Now I've got to do the algebra to figure this out, and unfortunately this is where many of you get stuck. Old school algebra people, you'll recognize that you just need to multiply both sides of the equation by 277. These two will cancel out, do the math, figure it out. Many of you, you like cross multiplying. That doesn't make sense to you. So when you cross multiply, you're going to take this number and put it up top. You're going to take this number, put it up top, and let's rewrite out what we would have. Again, trying to do all your work in your calculator is a surefire way to get things wrong. Take the time, use extra paper, and try to write things out. Of course, as I say this, I don't have enough room for my own work. All right, so there I have it rewritten out, just like we have it up here with cross multiplying. Now I can see this algebra is a lot easier for most of you. Divide both sides by 295K, divided by 295K. These two cancel out. I take this times this, divided by this, and I'm going to get 0.47 liters. So yeah, the balloon was 0.50 liters, now it's 0.47. It has gotten smaller because it's in a fridge. Okay, Sig Figs 2, Sig Figs 2, 2. That's correct, 0.47 liters. Let's look at the next one. Again, pause it. Give it a shot yourself. Now we have a crazy person who's not putting their balloon into the fridge. They're putting their balloon into the oven, which I think will result in a very stinky situation. But we're going to pretend that it doesn't melt. We're going to pretend this is some super kind of balloon. So here's V1 over T1 equals V2 over T2. So let's look at this balloon. Initially, it is at 0.40 liters. And initially, it's at 20 degrees. I've got to add 273 to that, so that's going to give me 293 Kelvin. Now I'm going to go ahead and put it into the oven, where I want to figure out what is that new volume, which I'm not sure what it is. I need to figure out what that temperature is. In the oven, it's going to be 250, so I got to take 250 plus 273, which gives me 523 Kelvin. Now I've got to go ahead and cross multiply, or again, if I want to do old school math, I could take 523K, 523K, cancel, cancel, and the V2 is going to equal these two multiplied by each other, divided by that. When I go ahead and do that, I'm going to get 0.71, and that already follows the Sig Fig rules of 2 Sig Figs, 2 Sig Figs, and, well, that has 3, but since these both have 2 Sig Figs, that answer wins. Next one, I got some chips, and they are sealed up. Now, I noticed that those chips seem like they get bigger when they're in a car on a hot day. So what I'm going to do is I'm going to take my chips, and there's 250 milliliters, that's the size of the bag, and they're at 19 degrees Celsius, which is a little cooler than room temperature. I'm going to put them in my car where it gets really hot, 60 degrees. That's way too hot. Okay, that's a really hot car. Don't go in there with degrees Celsius. That's blazing. So let's go ahead and find out what's going to happen. So V1 over T1 equals V2 over T2. Originally, the bag was 250 milliliters. Now, it's fine that I have milliliters here. I just know that on the other side of the equation, when I solve, I'm going to get an answer that's in milliliters as well. Temperature, though, we cannot leave it as degrees Celsius. I've got to take that 19, add it to 273, and I'm going to get 292 Kelvin. Now, going to the other side, when it gets hot, it's going to go up to 60 degrees, which is 333 Kelvin. I'm looking for that new V2. I'm going to go ahead and do my algebra. I'm going to go 333 Kelvin. I'm going to go 333 Kelvin. Cancel, cancel. I take this times this divided by this. And when I do that, I get an answer 28.51. Excuse me. Let's see here. 28.5. 285.1 milliliters. If I look at my Sig Figs, 4 Sig Figs, 3 Sig Figs, 3 Sig Figs, so I'm going to turn that to 3. That's going to give me 285 milliliters. So yeah, the bag gets bigger. It was 250. Now the bag is poofing out. If it gets too hot, the bag will probably pop. Next, we got a soda bottle. It's flexible. And we are going to take this empty soda bottle, a volume of 2 liters, 20 degrees, about room temperature, and I'm going to take it and put it in the freezer where it's really, really cold. So, again, I'm going to write out my equation. V1 over T1 equals V2 over T2. Looking at my initial volume, originally, that 2-liter bottle, well, it's a 2-liter bottle. And the temperature of that, it's 20 degrees. I add that to 273, and I get 293 Kelvin. Now, when I go to the other side, I've got to look at the new volume. That's what I don't know. I'm curious about. And I know the new temperature is going to be -4, so I add that to 273, and I actually get 269 Kelvin. Now I've got to do algebra again, so I'm going to do 269 times on this side, 269 Kelvin times on this side. These two can cancel, and again, I'm just taking these two numbers, multiplying them, dividing them by the bottom. When I do that, I'm going to get 1.836 liters. So yeah, that 2-liter just shrank. It got smaller because the lid's on it. And the gas is moving more slowly. Now, Sig Figs, I've got 2 Sig Figs. Oh, I only have 1 Sig Fig here, so I've got to turn that to 1. I'm going to keep that number. This 8 is going to round it up, so I get 2. Oh, this is one of those bad cases of Sig Figs. You're like, wait, we did a problem. The 2-liter got smaller, but actually when I applied Sig Fig rules, it looks like nothing happened to it. So, sorry, that's a Sig Fig blunder. Number 5. Some students believe teachers are full of hot air. You know I am. If I inhale 2.2 liters of gas at this temperature, 18 degrees, and I hold it in my lungs and it heats up to 38 degrees, what would the new volume of the gas be? All right, so I'm going to write out V1 over T1 equals V2 over T2. I'm trying to determine what happened before and after. Well, beforehand, I had 2.2 liters of gas in my lungs that were at 18 degrees. I add 18 to 273 and I get 291 Kelvin. Now, once it sits there in my lungs for a while, it heats up to 38 degrees. When I convert that to Kelvin, I get 311 Kelvin. Now, I've got to figure out what is that after volume. So, back to doing algebra. 311K, 311K. These two cancel out. I'm going to multiply these two numbers, divide by this number, and I get 2.351 liters. Okay? Sig Figs, 2 Sig Figs, 2 Sig Figs, 2. Well, it's going to be 2 Sig Figs, so I'm going to keep these two. And this 5 is actually going to cause it to rise up to 2.4 liters. So yeah, that gas used to be 2.2 liters. Now it's going to take up a space of 2.4 liters. Number 6. This is the same as all the other ones, but it changes a little bit. So let's see if you catch the change. We got a hot air balloon, and V1 over T1 equals V2 over T2. These are all Charles' law again. How hot will the 2.3 liter balloon have to get if I want it to expand to 400 liters? Okay, this is kind of ridiculous. Look at this. I got a balloon that's the size of like a 2 liter, and I want it to get ginormous. Okay? You're obviously going to have to heat this up a whole bunch. Okay, probably hotter than the balloon can handle, but let's see what temperature it would have to be. So originally it's going to be at 2.3 liters. The temperature is going to be at 25, which is 298 Kelvin. And I want it to get to 400 liters. That's 400 points, so that is 3 Sig Figs. Now I'm looking for T2. Now here's why this one is different. The unknown is on the bottom. So this changes things up. And I think for most of you, cross multiplying is going to be the easiest way to do it. You can't just multiply. If I put 400 here, that just squares the 400. That's not going to solve things. So I'm going to move this T2 up top, move this 298 up top. So over here, I'm going to rewrite out the problem. 2.3 liters times T2 equals 298 Kelvin times 400 liters. Now that I've got it written out like this, for most of you, you can see what you're going to do next. Divide by 2.3 liters, divide by 2.3 liters. And when you do this, you're going to find out the temperature would need to be 52,000 Kelvin. Okay, that's ridiculous. No balloon is going to withstand 52,000 Kelvin in temperature. But if you could have a balloon that would do that, yes, the balloon would expand from 2.3 liters all the way to 400 liters. And again, those are some sample problems with Charles' law.